Chemical thermodynamics. Thermodynamics is the change in energy that accompanies changes in matter. Now these are either physical changes in matter or chemical changes in matter. Usually heat is involved in thermodynamics, where heat is a measure of kinetic energy that relates to thermal energy. Thermochemistry is the chemistry which concerns itself with thermodynamics. In thermochemistry, we look at a number of factors. Energy is the capacity to do work. We measure energy as force across distance, or F times d, and generally it is measured in either joules or in calories. Heat is a specific form of energy. Heat is abbreviated with a lowercase letter q, and it is a measure of a flow of thermal energy that flows from areas of high temperature to areas of low temperature, where temperature is a measure of the average thermal energy within a substance. Now, kinetic energy is energy of motion. Everything like thermal energy, heat, mechanical energy, chemical energy, all of these are forms of kinetic energy. Kinetic energy has a mathematical formula of 1/2 the mass times the velocity squared. Thus, the higher the mass, or the higher the velocity of a substance, the higher its kinetic energy will be. There are various subdivisions of kinetic energy, as I said: heat energy, electrical energy, chemical energy, mechanical energy. Potential energy is the other form of energy that exists in the universe, and this is energy of position or composition. For instance, if something is more elevated in space, holding it up higher, the force of gravity pulling on that is going to be a greater acceleration when it reaches the ground level. So there's an overall increase in the potential energy associated with that. If you think of a roller coaster starts at the top of a large hill, and the conversion of the potential energy from that point in space into kinetic energy as it moves down the hill is what drives the roller coaster forward. Remember that energy can be transformed easily between different forms. It can be transformed between kinetic energy and potential energy, and it can be transformed between different types of energy, for instance, between heat and electrical and chemical and mechanical, etc. Now, there are two different types of processes that occur in chemistry. There are exothermic and endothermic processes. These tend to relate to heat, where heat is kinetic energy that moves from high to low temperature. If a process is exothermic, you will start with a higher temperature, or higher energy rather, and end with a lower energy. If I have a reaction, for instance, the beginning of the reaction where the reactants are will be higher energy than the end of the reaction where the products are. For example, the combustion of methane, which occurs, as you see below, produces 890 kilojoules of energy. An endothermic process is one in which the products are higher in energy than the reactants, so there is a gain in energy overall, something like the melting of water, where a solid water has to absorb 6.02 kilojoules in order to be transformed to liquid water. Energy is thus either a product or a reactant in our equation. If it is a product, the reaction is exothermic. If it is a reactant, the reaction is endothermic. Now, thermochemistry, thermodynamics, are governed by specific laws. The first law of thermodynamics states that the combined amount of matter and energy in the universe is constant. This is a restatement of the law of conservation of matter and energy that we've talked about in the past, E equals mc squared. This is the reason why a perpetual motion machine fails, because energy is always lost or gained in a process so that it is overall conserved. We cannot create energy out of nothing, so a motion machine cannot constantly create energy. Because all energy transformations are less than 100% efficient, a machine cannot also maintain the amount of energy that it contains, so it will always lose energy slowly as it operates, and thus will never be able to continually operate infinitely. Now, in studying thermal chemistry, we need to have certain parameters involved in what we study. There are 3 different vocabulary terms that we use in order to govern this. The system refers to the situation that is in question. The surroundings are the remaining conditions that exist besides the system. The universe is a combination of the system and its surroundings. The system, thus, is part of the universe in question. State functions are a reference to a particular state of a system. Every system has a particular thermodynamic state. This relates all of the conditions that govern the system: its pressure, its volume, its temperature, composition, physical state, etc. Every piece of the state is referred to as a state function. For instance, pressure is a state function, volume is a state function, temperature is a state function. These reference the state of the system. Now, they are independent of the pathway that a system will take to change its state. So if I'm moving from one particular value of the state function to another value of the state function, I can do this by a number of different means. And the particular means by which the process uses to get to that end value does not determine the value of the state function. It's kind of like climbing a mountain. If you have a mountain that has a winding path that winds up the mountain that is, say, 12 miles long, versus climbing straight up the face of the mountain, that would be, say, a 5-mile climb. Both of these end at the same point, but there are two different pathways to reach that point. The state function dictates net changes in the state, and we represent these with the letter x. So the change in the state function, or delta x, is equal to the final state of the system minus the initial state of the system. And this will always be the case in what we deal with in thermochemistry. There will always be the final conditions minus the initial conditions. Changes like heating and cooling are not state functions. These are processes which can bring about state functions by causing specific changes. Heating something can change its temperature. If I change its temperature, then I change its state function. But the heating itself is not a state function. Internal energy is the total amount of energy that a substance contains. This is a combination of the kinetic energy in the substance, the potential energy in the substance, all of the intermolecular forces, all of this combined. We abbreviate internal energy with an italicized capital E. Changes in internal energy are the internal energy of the products of a process minus the reactants of a process. If the delta E is positive, energy is absorbed in the process, and therefore the process is endothermic. If the delta E is negative, then energy is released in the process, and the process is exothermic. The delta E then measures energy change which occurs between the system and its surroundings. If energy is absorbed by the system, then it is taking energy from its surroundings. If energy is released by the system, it is giving energy to its surroundings. So in the case of an endothermic process, the surroundings will cool. In an exothermic process, the surroundings will heat up. The change in energy of the system, then, is going to be equal to the opposite of the change in energy of the surroundings. The sign of the delta E relates the exothermic endothermic process then. So negative delta E system is exothermic. And in this case, the change in energy will be written as a product. If we look at a equation like this, CH4 gas plus oxygen gas produces CO2 gas plus water gas, it has a net exothermic release of energy of 890 kilojoules. Likewise, we can write an endothermic reaction where the change in energy is written as a reactant. CO2 plus water plus 890 kilojoules produces CH4 plus O2. This is simply the reverse process of the reaction that is given above. Now, changes in internal energy relate heat and work. Heat is the thermal energy difference that is caused by changes in temperature between areas of high temperature and low temperature. Work is the thermal energy difference that is produced by movement against force. So force times distance is work. The change in energy of the system, then, is the final energy of the system minus the initial energy of the system, which will be the energy of the products minus the energy of the reactants. And this will equal a combination of the heat and the work, Q plus W. So if I have a positive heat, then I'm absorbing heat. My process is endothermic. If I have a negative heat, I release heat, which means my process is exothermic. A positive W means that work is being done on the system by its surroundings. For instance, my system is being compressed, as an example. The negative W is that work is being done by the system on the surroundings. For instance, I'm expanding. Because energy is a state function, the same change in the energy of the system can be achieved by different combinations of heat and work. Adding or removing energy by changing either heat or work changes the overall energy of the system by the same amount, which is another expression of the first law of thermodynamics.